Hey Phyz C kids, Campbell here. In our second summer assignment video, we're going to talk about some calculus. So calculus is just the study of change. And in physics, we study lots of changing things. We study changing position and velocity and energy and momentum, but we've never been able to study things like changing acceleration, changing forces. With calculus, we can do that. Now, there are two branches of calculus united by the fundamental theorem of calculus. The one we're going to talk about in this video is differential calculus, which is the rate of change or slope. It's just taking a derivative is a fancy way of saying taking the slope. In our second video, we're going to talk about integral calculus, which is just the area under a curve. So every time in Physics 1 you took the slope to construct a graph, you were just taking a derivative. In fact, the derivative of a position versus time graph, or the slope of a position time graph, remember, gives you velocity. So let's say we chucked an alligator off a bridge, and here's our graph of position versus time. So if I want to construct a velocity versus time graph, right, I just take the slope, which is taking the derivative. So I would look at this graph and say, well, it starts off with some positive velocity, which decreases, right, as the slope decreases to 0. So here I'm going to have a 0. And then I get back to the same velocity, right? Up-down rules. So here that same would be the same velocity, and then that velocity is going to increase as the alligator maybe lands in the river below the bridge. So we start off with some positive velocity. Here at 1 second, where we have the same magnitude of that velocity, just negative. Oops. And then it keeps going because it's going to land farther beneath than we threw him off the bridge. We don't want him to land by our feet because he might eat us. So that's not a very good straight line, but there would be our slope. And if we took another slope, right, from our velocity versus time graph, remember we get acceleration, right, meters over second squared. And that's actually called a second derivative of position versus time. It's just the next derivative, the next slope. What would that slope be? Well, it's negative. Curvy goes to slanted, slanted goes to flat. So we have a flat, oops, that's a flat line there. And if this is in free fall, right, that would be negative 9.8 meters per second squared. Gosh, these graphs are horrible, aren't they? Sorry. So velocity, right, is position over time. That's really just the average velocity, right? If I wanted to know what the average velocity was from here to maybe this point right here, right, if we did rise over run, right, it would just give us that, which is an average, and that doesn't tell us a lot about this alligator we're throwing off the bridge. If I wanted to know about what the instantaneous velocity was, say here at 0.25 seconds, right, we do a tangent line. Or if I wanted to know it at 1 second, right, again, we do a tangent line. Well, that's really just taking a derivative. So in calculus language, our instantaneous velocity would be equal to dx over dt. So we take the derivative of position with respect to time. And all those d's, right, notice the d's just replaced the deltas. It just means that the time interval for the slope is 0, super teeny small. So that means that my acceleration is equal to the derivative of velocity with respect to time, or the second derivative of position with respect to time. So derivatives, just slope. So let's go to math language. So let's say we have some function, 3. So if we made a graph of y equal to 3, right, here's my y equals 3 line, what would the slope of that be? So if we take the derivative, right, which is just taking the slope, sometimes called f prime or y prime, what would it be? Well, obviously there's no slope, so that's 0. What if our function was x? So let's make a graph of y equal to x here. What would the derivative of that be, or what would the slope be? Well, clearly it goes up 1 over 1, so the slope is just 1. Well, what about 2x? We make a graph of 2x, right? That's just a steeper x graph, because now the slope is 2. And let's go a little fancier. What if we had x squared? So here's a graph of x squared. And what would the slope of that be? Well, if we think about it, we have a negative, right? And that slope decreases. It's a negative slope. It's decreasing to 0, and then it's increasing at the same rate of change. So if we made a graph, if we calculated the slope and plotted it, we would actually find that the slope of that is actually 2x. So the derivative of x squared is 2x. What about x cubed? Well, here we have a positive slope that goes to 0 and then increases in the positive. And you know what that is actually? The derivative of that, or the slope of an x cubed graph, is actually 3x squared. Do you notice a pattern? When I have just x, the number, my derivative is just the number in front, the constant in front. When I had x squared, it became 2x. When I had x cubed, I have 3x squared. Well, there's a rule. It's called the power rule for derivatives. And all that says is the derivative of x raised to a power, you bring that power in front, and then you have x raised to the power of n minus 1. So if you notice, right, we took the 3 out here and we put it in front. And then we subtracted 1 from 3 and we got 2. So, power rule for derivatives, not bad. What if we have two things like this, x cubed plus x to the 5th? Well, that's called the sum rule. There's also a difference rule if that was a subtraction, but really makes no difference. You just do the derivative of both. So here's our x cubed, so we bring the 3 out in front, and then we subtract 1 from that, so that's 2x. And then we do the same thing here with the 5x, or x to the 5th. We put the 5 in front, and we subtract 1, and we get 4. Pretty cool, huh? That's the power rule for derivatives. Now, I'm just going to tell you this because your math teachers, if you're just taking calculus now, your math teachers are not going to be happy because you're going to want to just skip right here. And they're going to take you through why this is the case in a very long and painful and tedious way. And you're going to want to be like, hey, but Mrs. Campbell, so don't say my name. I did not teach you the power rule. You do not know the power rule, but you could use it to check yourself. Because Schneider and Loeffler are not going to be happy. Now, let's take a derivative. So let's do this. I want to know the derivative of y as a function of x for this function right here. So our dy dx, we bring the 3 out in front, right? So we're going to have 3 times 3, and then we have our 3 minus 1, right? So that's 2, plus we bring out the number in front, which is just 1, right? Because if this is just x to like the 1 power, 12, and then x, and we have 1 minus 1, right? So what does that give us? 3 times 3 is 9, x squared plus 12, because 1 minus 1 is 0, right? X to the 0th power is just 1. All right, now that we took the derivative, we could find the slope of the tangent line. So instead of like trying to plot it on a graph and get the rise over run, we can just plug in 2 here now. So the slope of our tangent line, we're going to take 9 and we're going to put 2 in for x, and then we're going to add 12. So that's 9 times 4 plus 12 is equal to 48. Boom. Slope of the tangent line. So if this was a position function, we'd now have the velocity at 2. Pretty cool. What about trig functions, right? In physics, we use a lot of trig. Well, if we took the slope of a sine graph, what would we get? Well, here we have a maximum slope, right? That's called an inflection on a graph because it's the maximum slope, and it's a positive. So on our position, or on our derivative, our slope, right, that would be a maximum positive. Here we have 0 slope, so we'd be at 0. Here we'd have an inflection again, so we have a maximum negative, and then here we'd have a 0. The derivative of a sine graph is just cosine. Derivative of sine is cosine. Well, what if we take the derivative of cosine? Well, let's look here. So here we have 0. 0. Here we have our inflection point, right? So that's a maximum, but it's negative, so that'd be down here. And then we have a 0. And then we have an inflection point here, but this is positive, so that'd be positive. So guess what that is? The derivative of cosine is negative sine. Let's keep going. What's the derivative of negative sine? Well, guess what that is? Negative cosine. And just, for completeness here, what is the derivative of negative cosine? That's just sine. Interesting. Now, on your equation sheet that you get for all your tests and on the AP exam, they have some calculus on it. This is what they give you. This is actually called the chain rule. Hopefully you'll learn about the chain rule before we have to do it in physics, but if not, I'll teach it to you then. Here, of course, is the power rule. And here's a couple. Here, if you have an exponential function, the derivative of an exponential function, the constant comes out front, and then this is just the same as this, right? Interesting. The derivative of a natural log is just 1 over x, and then here's our sines and cosines derivatives. All right, so let's get to physics. What is these derivatives? We already talked about slope, but how does this apply to, say, kinematics? Well, let's say we have a constant acceleration. If we have a constant acceleration, that means that our position is changing as a function of t squared, right? So that would be a nice little parabola. So we said that the derivative of that would give us velocity, right? Because the slope of a position versus time graph gives us a velocity graph. Well, let's take the derivative of position with respect to time. So this here is just 0. We take the derivative of this, right? We subtract 1 and we move the number in front, which is just 1, so that's VO. And we take the derivative of this, right? And that would be, we bring the 2 out front, so it's 2 over 2. And then we have A, and then we subtract 1 from here, right? And that just gives us T. So that gives us that velocity is VO plus AT. Huh! Looks like a familiar equation, doesn't it? In fact, if you were in my Phys 1 class, you'll know I call that my favorite equation. And in fact, the graph, right, curvy goes to slanted, the graph would look like this with, of course, there's some, maybe the initial velocity is 1, so maybe it looks like that. I don't know. But there's our velocity graph. Well, the second derivative of position versus time is acceleration. So if we take another derivative of this with respect to time, right, that just becomes a 0. And then minus 1, right, that just gives us A. So our position versus time graph gave us the derivative, which was velocity, and we took another derivative that gave us an acceleration, and slanted goes to flat. So remember, if you had me in AP Physics 1, I always had that chant: curvy goes to slanted, slanted goes to flat, flat goes to 0. All we were doing was taking derivatives. So notice as you differentiate, things get simpler. We went from something complicated, what I call my least favorite equation, to my favorite equation, to really no equation. So the derivative of position gives us position versus time gives us velocity. The derivative of velocity versus time gives us acceleration. And the derivative of acceleration is called the jerk function. And then actually there's snap, crackle, pop, but we won't talk about those. Calculus also gives us another tool for solving problems. For example, you throw a ball upwards from 2 meters with some initial velocity, and we want to know the time to reach maximum height and what the maximum height is. Well, if we use my least favorite equation, all right, we would use XO plus VOT plus 1/2 AT squared. Obviously, we can't solve this directly because we have 2 unknowns. In fact, if we plug in our numbers, right, our final position is we start at 2 meters with an initial velocity of 15 times t plus 1/2. Now, this is free fall, right? So that's negative 9.8, but let's round 9.8 up to 10 just because it makes our math a little easier. T squared. So remember that velocity is 0 at maximum height. So what if we take the derivative of this function? That would be 0. That would just be 15 plus, right, that's negative 5, right? So we bring the 2 in front, so that's a negative 10 times t. And since velocity at maximum height is 0, we set that equal to 0, and we solve for t. So we would say that would be 15 is equal to 10t. So time is equal to 15 over 10, or 1.5 seconds. So, I mean, yeah, we could have done that using our normal equations, but that's another way to look at this. And then what's our maximum height? Well, we can just go plug this back in up here, and we can say that that's equal to 2 plus 15 times 1.5 minus 5 times 1.5 squared. And so if we do that math, we're going to get 13.25 meters. So using calculus is just another tool we have in our toolbox for physics. So let's do one more problem. Here is another position equation for a particle, and you'll notice this one we can't do the old way. We can't use the normal kinematic equations because this time we have a t cubed and not a t squared. So in this case, I want to know the velocity and acceleration at 2 seconds. So first thing we want to do is we want to take the derivative of this. So velocity is the derivative of position with respect to time, so dx over dt. So that would be a 0. This would be just 9.2. And then we bring the 3 in front. 3 times negative 2.1 would be 6.3 t squared. So there is our derivative of that equation. So that means that the velocity at 2 seconds, all we got to do is just plug in 2 seconds for t. So we go 9.2, whoops, that's supposed to be 0.2. Velocity is 9.2 minus 6.3 times 2 squared. And so if we solve that, we'll find that the velocity at 2 seconds is negative 16 meters per second. And the next question said, is that constant or changing? Well, obviously, because of this t here, anytime the time changes, the velocity is going to change. So this is a changing velocity. Okay, well, you know, we had changing velocities before, no big deal. How about acceleration? So if we take our second derivative, acceleration is the second derivative of dx dt. And so we take a derivative of this, that becomes 0. We bring the 2 in front, 2 times 6.3, and that becomes just t. So our acceleration equation then is 12.6 times t. And so at 2 seconds, the acceleration at 2 seconds is then going to be 12.6 times, oh, there's a negative. Sorry, that should be a negative. Whoa, dang negatives. Times 2, which gives us a negative 25.2 meters per second squared. Oh, almost forgot the negative. Now, is that changing? Well, yeah, because as t changes, the acceleration is going to change. So this is one that we could never have done in Physics 1. Now, next question, what time does the particle stop? Well, what's true about velocity when a particle stops, right? It's just 0. So we're going to go back up to this equation here and set it equal, well, I should say this equation here, and we're going to set it equal to 0. So 0 is equal to 9.2 minus 6.3 t squared. All right, so we do a little rearranging. We get 6.3 t squared is equal to 9.2. So that means t is equal to the square root of 9.2 divided by 6.3, and we get a time equal to 1.2 seconds. Coolio, right? Calculus sometimes makes physics a lot easier. So work on that worksheet. If you have any questions, drop me an email.